How did this get here? Didn't we just order it like a few hours ago?
When my older daughter asked that, I stopped for a second because it is a simple question with a surprisingly deep answer. Somewhere between a tap on a screen and a box on our doorstep, invisible systems spin up, data races across networks, decisions get made in milliseconds, and the physical world moves. It's fascinating to think what happens when you stream a song, book a hotel room, reserve a flight, or open an app and just expect it to work. All this technology is so fun, and I love working in this industry. I've spent my career building software and systems that make up the internet. I was CTO at Shopify and ServiceNow, and SVP at Slack, an early engineer at Cisco Systems, and now I'm CTO at Webflow. I've helped build data centers, protocols, software, and services, and led global teams along the way. This podcast is for anyone who wants to understand how our modern world actually works, not just shopping and delivery, but the invisible machinery behind nearly everything we do. It is for anyone who's ever wondered, how did this get here? Or how did that actually happen? I'm excited to take you on a journey, to take these layers of technology apart and explain them in a clear, grounded way. You probably think you connect to Wi-Fi, you're on the internet, and away you go. Well, I wish it was that simple. I'm Alan Meinwand, and welcome to Pixels to Packages. Hi everyone, I'm Alan, and in this podcast, we're going to pull back the curtain on modern life. Not at a buzzword level, but at a real physical and technical level. We're going to follow the journey from the moment pixels change on your screen to the moment a package shows up at your door. In this first episode of Pixels to Packages, we're going to stray pretty close to home. We're not going to talk about internet routing or data centers or warehouses or delivery trucks, not just yet. We're going to focus on what happens the instant you open a browser or an app and try and reach something on the internet. We'll get to all those other things. There's so many things to talk about in future episodes. So much cool technology here. It's going to be a lot of fun. So, picture this. You open up your laptop or you unlock your phone. Display lights up, millions of pixels snap into place. They form icons, text, images, all sorts of things. You tap a browser or an app. It feels almost like instantaneous that something begins to happen. And that's actually happening as an enormous number of systems are sort of waking up to do things. Your operating system immediately goes to work. It schedules tasks across processors, allocates memory, manages storage, connects to the network. It's making decisions millions of times per second to keep everything working. And without all that orchestration, nothing else even gets a chance to get started and connect to the network. On top of that, the browser, the app, begins its own choreography, its own little dance. Before it can show you anything, it has to answer a deceptively simple question. Where on the internet is the thing you are trying to reach? So you might type a name like a shopping site or tap a bookmark, but computers don't really understand names. They understand numbers. More precisely, they understand binary, ones and zeros. But humans, at least most of them that I know about, don't talk binary. So the translation of names to numbers, specifically to something called Internet Protocol or IP addresses, defines where the site you're trying to reach is located on the big internet. And to figure out what that address is and where that site is located is a job of DNS, or the Domain Name System. DNS is the first step in the Pixels to Packets journey. So when your device needs to resolve a domain name, it doesn't just look it up in one place. It walks this hierarchy, this tree structure that sort of mirrors how the internet is organized. At the very top of that tree, of that hierarchy, is the Internet Corporation for Assigned Names and Numbers, or ICANN. ICANN is an organization responsible for coordinating the global domain name system, the system that maps names to numbers. And ICANN oversees what's called the root zone that defines the highest level of the internet's naming structure. You all know what these names are. These are the .coms, the .nets, the .edus, the .govs. So the first thing is your device asks DNS what's called the resolver that's often inside your operating system. And it asks the resolver to figure out where is Amazon.com, or where is Spotify.com, or where is colorado.edu. And if the answer isn't local already, it's not already cached on your machine, the resolver asks for a root server. That root server is run by ICANN. And the root servers sit at the top of the DNS authority, the .net, the .com, the .edu. These servers don't know where individual websites or applications live, but they know where to find the servers responsible for the top-level domains like Amazon.com or Spotify.com. So the root server points to a resolver at the top-level domain server. That server in turn points to the next level down the tree to an authoritative server for a specific domain, like Spotify.com or Colorado.edu. Finally, one of those authoritative servers responds with an IP address, a 32-bit grouping of ones and zeros. That's a numerical destination that routers actually send packets to. This entire process is global, distributed, redundant, and in certain cases heavily cached, which means it's stored local to you. So even though it sounds like we're talking to multiple servers, something run by ICANN, something run by Amazon, something run by Spotify, something run by a university, it's all globally distributed and it happens in milliseconds, thousands of seconds. And eventually your device gets an answer back. It says, I know where Spotify.com is, I know where Colorado.edu is, and you have an address. You have a 32-bit address that tells you where to go on the internet. Now, we're going to talk a lot more about IP addresses later in different episodes of this podcast. But for now, think of it as a number or a street address on the global internet telling your device, your phone or your laptop, where to connect to. Now we get to the thing that actually moves across the internet, and that's packets. Everything your device wants to send, a web request, an image, a payment, a message, is broken down into small little pieces called packets. A packet is a chunk of data small enough to move efficiently across many different networks, routers, physical links, satellite links, fiber links, cable links. The internet doesn't really send messages, it sends packets. And millions and millions and millions of these packets every second are moving independently across the internet at any one point in time. So DNS tells us the address of to send the packets to. But knowing where to send the packets to is only really part of the story. It's like knowing a street address. Your device also needs to know how to structure those packets so they can make it across the internet from point A to point B, from your device to that application or to that site you're trying to get to. This is where multiple layers of protocols come in. Because the internet is not really one system. It's a stack of layers, each responsible for an individual job, all working together while at the same time working independently. At the foundation of that is IP, or the Internet Protocol. As we just learned, IP gives every packet an address, and it tells routers where to route the packets to. It answers one very narrow question. Where should this packet go from your device to what destination? IP actually doesn't guarantee the delivery, the order, or the timing. It simply moves the packets from location 1 to location 2. On top of IP are two things called transport protocols. Well, there's two basic transport protocols. One is called TCP, or the Transmission Control Protocol. And TCP is all about reliability. TCP wraps IP. We'll talk a little bit more about that in a second. And it wraps IP in a way that makes sure these packets go from point A to point B in a dependable way. It numbers the packets, it waits for them to go from point A to point B and get acknowledged, and it resends anything that might have gotten lost along the way. This is what makes loading a web page or submitting a payment feel solid, feel like a connection, rather than a set of scattered packets you put on the internet and hope that they all get there. The other protocol that sometimes is used alongside of IP is UDP, or the User Datagram Protocol. There's a lot of acronyms in this podcast. I'm sorry about that. We're maybe at a glossary or something. But the User Datagram Protocol is a different trade-off. It sends packets without waiting, without acknowledgments, or without retries. If packets are lost, they're lost. I know that sounds kind of scary and dangerous, but for audio, video, and real-time systems, it would be a lot worse than waiting for packets to be retried. They just resend anything that happens to get lost. So speed matters more than perfection and making sure things are always in order. So there's TCP that forms connections and UDP that forms streams of data that may or might not be super lossy. Both TCP and UDP are on top of IP, and they can all be wrapped in yet another layer of security like TLS, or the transport layer security, that secures all this data and keeps packets private as it moves around the internet. Now, I've just gone through a lot, things that people spent their entire careers on. But this layered structure is one of the most important things to understand how pixels turn into packages, and that's encapsulation. So DNS is about names to numbers. Packets is about dividing things into small pieces to be transmitted across the internet. TCP and UDP wrap that up and either form a reliable or an unreliable session between two devices. But all that leverages encapsulation. So you can think of packets kind of like letters moving across the global postal system. When you send data across the internet, it's not set as one continuous stream. It's broken up into packets, each like an individual letter dropped into a mailbox. Think about this. If you mail 2 letters at the same time to the same place from the same mailbox, there's actually no guarantee they'll arrive in the order you send them. They may travel through different sorting centers, take different routes, different mail trucks, different planes, different trains. They might arrive minutes, seconds, days, or weeks apart. Packets behave the same way. Each one moves independently across the network, taking whatever path is available to them at the time. The path they take is yet another set of protocols called routing protocols, and we'll get to that someday too. Now, once you have those packets put into the internet, making sense of that jumble is the responsibility of the layers I've already mentioned, the transmission control protocol or the user datagram protocol, or maybe even application logic, but that's another detail. These layers handle the ordering, the timing, and the reliability. TCP, as we said, keeps track of which packets belong together and reassembles them. It's kind of like taking 2 letters, putting them in a mailbox, wrapping them with something else, and saying, read letter 1 before you read letter 2. UDP would be sort of like putting 2 letters in a mailbox and letting them arrive whatever order they're supposed to arrive in, or whatever order they do arrive in, and letting the end user try and figure out, is this page 1 or this page 2, and putting it back together again. So, as packets move up and down the protocol stack, as things go from names to numbers, and then get wrapped in TCP or wrapped in UDP, and then wrapped in IP, this encapsulation idea is so incredibly important because it allows every individual piece of software, every individual layer to have its own job. Now, back to your laptop or your phone. You've just opened up your laptop or your phone. You said, I want to go to Spotify.com. I want to listen to some music. Well, that does DNS. Probably wraps it up in UDP, finds out the IP address of Spotify, and then it actually goes forth and puts it on your local network. Now, that local network is something like your Wi-Fi network, or if you're using wired, it's something called Ethernet, which is another technology that would take things from your local device to your home router. We're going to talk a little bit about that now. But the important thing to remember about encapsulation is no single layer understands the entire journey. Each layer reads the envelope only meant for it. TCP talks to TCP, UDP talks to UDP, IP talks to IP. And when the packet reaches those destinations, each of those envelopes is peeled away and understood by the destination. So think of it again like this way. Your laptop or your phone takes the data, wraps it up in TCP or UDP, wraps it up in IP, a letter in 2 envelopes now, wraps it up in Wi-Fi or Ethernet, puts it out on your local Wi-Fi network or on your local wire. It's going to travel across the internet, and at the other side, it's going to pull those wrappings, those layers, those encapsulations apart to make sure that everything is handled logically. Because everything is packetized, the system is remarkably resilient. Typically, if only one packet is lost, only that packet needs to be resent using TCP. Nothing else has to be start or stopped or restarted. This is why the internet scales, why it survives failures, and why it keeps working even when parts of it breaks. So once your device has packets ready to send, they need to leave your home. In most cases, that happens through your local Wi-Fi. So what's that about? Well, your local Wi-Fi might form its own mesh, or it might be a single radio signal that connects to your laptop. Your laptop or mobile phone connects digital bits into radio waves, modulates those signals that travel through the air at 2.45 gigahertz. That's the frequency. Those signals are received by your Wi-Fi router. Now, your Wi-Fi router isn't a dumb box. It's a computer with its own processor, memory, and operating system. It assigns local IP addresses. It's got its own IP address, that 32-bit number. It looks at active connections, and it does something called network address translation, which essentially takes all the things happening on your home network and makes it appear to be an address on the global internet. That router is your gateway to the internet. It's the edge of your private world and beginning of the public one. Once packets pass through it, they're on their way across the internet to their destination. So from tap to gateway, this entire journey takes less time than a human can even consciously notice. I'm going to say this term a lot. Milliseconds, tiny, tiny fractions of seconds is how long this takes. Think about it. From the time you type www.amazon.com and get that first page back, or www.spotify.com and start hearing that first stream, it feels like it's less than a second. And everything I've talked about so far is one small little piece of that. So we're talking about fractions of seconds here. Now, let's imagine that your home device, you've gone through DNS, you've wrapped it in TCP or UDP, you've got an IP address, you've done those layers of encapsulation, you've gone across your local Wi-Fi, and you've put those packets on the internet via your local router. Eventually, and we're going to talk about how this happens in a future episode, there's so much tech here. Eventually, those packets arrive at a data center. So a data center is not a cloud. It's actually a real building. So picture like a Walmart-sized space filled with racks and racks that are in these long rows of computers. Inside each of these racks are shiny and skinny 19-inch wide servers that are sort of stacked vertically, like stacked up. Each server is a computer with CPU, memory, storage, networking cards, and the building is packed with power systems, cooling infrastructure to make sure this thing doesn't overheat, and an astonishing amount of fiber and cabling, like miles and miles and miles of it. I've helped build dozens of these facilities around the world, and every one of them is a minor miracle of coordination. Power, cooling, networking, telco, trenching, generator power, software, all have to work continuously and without interruption. And in most modern systems, there's not even just one server or one data center. Even these systems are globally distributed. Your request might be handled when you put that packet on the wire and it goes through your local router. That might be handled by a nearby data center or by machines thousands of miles away, depending on load, performance, or what's available at this moment in time. In many cases, the server responding to you, and I say kind of server in air quotes, is not even a physical machine at all, but it's a logical one played out by software running across clusters of machines that's balanced by something called a load balancer, which takes your request, comes in as it comes in, and figures out which machine can handle it the fastest. That system decides which server in those racks and racks of servers can handle your request. And once the server receives it, runs that application code, it fetches data, it pulls things from databases, and it makes a response. At the same time, other systems wake up. Web pages get assembled, payments are authorized, inventory is checked, orders are created, all of these different systems and processes are packets with encapsulation going out across wires. And all of that can begin while you're just sort of still staring at the screen. You haven't even started to think about the song you're going to listen to or the thing you're shopping for yet. And all this has already happened. Once the server's done its work, it's figured out what you're looking for, everything we talked about just happens in reverse. It goes from the server in the data center all the way back to your local phone or your local laptop. The response generated in the data center is broken into packets, wrapped into layers of encapsulation, and sent back across the network towards your device. Each packet again travels independently, possibly across different routes, handled hop by hop, where every layer looks at those various layers of encapsulation. When those packets arrive at your laptop or phone, the layers are peeled away, and the original application data is given back to your application of the browser. And then what feels like a single smooth response that you see is actually thousands of tiny coordinated steps happening at once. At that layer, the response is usually sent using something called HTTP, or the Hypertext Transport Protocol, riding on top of TCP or UDP. Those details matter, but kind of what really matters right now is the result. What comes back to your laptop isn't really a picture of a website or a song. It's instructions and data. Things that come back in a formatted set of data, something called HTML, or Hypertext Markup Language, cascading style sheets, or CSS, and JavaScript, sometimes along with images, fonts, and assets. So when that data comes back, HTML describes the structure of the page. How does that website look? How does that app get displayed? CSS describes how the elements should look, their size, their color, their position, their layout. And JavaScript contains sort of programmatic language and logic and behavior for what happens when you click or scroll or see animations on the screen. These files travel back across the internet as packets. They then get processed by your browser application before you even know it. And then the browser gets to work. It takes all this data and produces the thing that you see on the screen. And all this feeds into what's called the browser's rendering pipeline, which turns abstract instructions into those pixels. We've come all the way back to pixels. At that moment, the loop is closed. A server in the data center has sent back the raw ingredients, packetized and encapsulated. That HTML, that CSS, that JavaScript is being rendered, or that application is interpreting that data, and it's turning them into something you can see, something you can touch, something you can use. This is where all the pieces, everything I've just talked about, starts to come together. Because in the next layer of the journey, those instructions become layouts. They become boxes, texts, buttons, images, animations, menu bars, things that you can touch, motion. So in the next episode of Pixels to Packages, we're going to dig into those areas. We're going to dig into HTML, CSS, JavaScript, the box model, how data is pulled from the internet and becomes the pixels you interact with every single day. And this is where episode 1 really lands. It's kind of incredible that, honestly, any of this works at all. In far less than a second, often just milliseconds, your request travels from a screen in your hand to a data center somewhere in the world using an IP address and routing and TCP and domain name system. It triggers databases, it triggers software, networks sort of pass your data around without you even knowing. There's business logic for payments and inventory checks and songs you might be recommended. This happens billions or trillions of times every minute, every day across the global internet. Even this podcast, streaming to your device right now, is riding on packets, encapsulation, and all the protocols and 3-letter acronyms we just talked about. Audio data is broken into packets, wrapped in layers, routed across networks, reassembled, Pieces are replayed and retried if they got lost. They're decoded, they're played back, all while you're barely aware any of this is happening. If you visit my website, www.pixelstopackages.com, you can pause for a moment and sit with the magic of it all, asking yourself that simple question that started this journey. How did all that just happen? In the next episode, we're going to turn around and follow the data back in more detail. We're going to explore how servers send their responses, how browsers receive packets, and how raw bytes become pixels all over again. We're going to talk about JavaScript engines like V8, the box model, how images are decoded, and how modern browsers orchestrate all of this into that web app, that application, that web page that you're seeing. Because before a package can ever move through a warehouse, the network, the servers, and the pixels have to come alive. It's so exciting to see this happen. And when you start to see and understand these hidden systems, you'll understand how they help us in every aspect of modern life. I'm Al Monwant, and thank you for joining me for the very first episode of Pixels to Packages.